So what is the formula, firstly, for this tangent line that was created from this initial guess? Well, the tangent line is occurring at x naught, f of x naught, right? So that's a point we know is on the tangent line. Simultaneously, we know that the slope of the tangent line must be the derivative of this function, right? The slope of this function at x naught, right? So we now know x naught, f of x naught is on the first tangent line. And we also know the slope of the tangent line is f prime of x naught. Okay? So with those two, we can construct the tangent line in the abstract. We don't have to pick particular values. I'm trying to do this generally speaking. So the tangent line itself should be y minus y1, right? The variable y for the line itself, minus the y value that we know is on here, so f of x naught, equals the slope, that's f prime of x naught, times x minus the x coordinate, which we know is on this, the first coordinate of the point which is on this line. So minus x naught, there. Right, there's our tangent line. That's the first red tangent line. And now we want to know, where does it hit the x-axis? I want to solve for x1 here. I don't know what this is. So to do that, solve this line for its x-intercept, right? Every oblique line has one. So we want to find this x-intercept, so we should make y 0. Okay? Solve for tangent lines x-intercept. So to do that, like I just said, we'll set y equal to 0 and solve for x. This x we're going to find right now is x1, the next approximate to a. Okay, so we'll have 0 minus fx naught equals the derivative at x naught times x minus x naught. All right, so I should just, that's gone, I should just divide off by f prime x naught over here. So we'll get negative f of x naught divided by f prime of x naught equals x minus x naught. Adding x naught to both sides, I'm going to reverse the positions just to make the formula look clearer. So this would give us that x is equal to, and I'm going to put this stuff on the other side. I'm adding this over here, so it would be x naught positive minus, that's this minus here, fx naught on the derivative. At the same location. All right. So now we have our formula. Right? If I wanted, for any particular function, if I picked an initial guess, I could plug that initial guess right into this formula right now. Right? Whatever function we started with, whatever initial guess I want to select, as being close to a, I'm trying to find out about. And this little formula would produce nothing other than x1. Right? It would give me this x-intercept, right, to that first tangent line. If I do this again, right, if I take that number and plug it back into this formula, right, then that means x2, the next one down the road, right, even closer to a, it's hard to see there, but even closer to a, would be x1, right, just fill in this formula with x1, the value I just calculated. So f of x1 over f prime of x1, and so forth and so forth. And I could keep applying that value. I'll take that value x2, plug it back into the formula again, I'll get x3. x3 again, I'll get x4, and so forth. And it will keep giving me more and more x-intercepts of tangent lines closer and closer to a, giving me better and better approximates to a. Okay? So therefore the formula is that the n plus first approximate to a is going to be the previous approximate minus the function at the previous approximate divided by the derivative at the previous approximate. Okay? So it's an iteration scheme. Keep applying the next value that you get, apply it back into the same formula again, it'll put out a value even closer, and you can get as arbitrarily close as you would like.